Welcome to this next video in the playlist on ring theory. In this video, what we're going to discuss is the construction of the fraction field, or the field of fractions, for an integral domain. Okay, so let me begin with the basic motivation for what we're going to do here. Okay, so we're going to start off with some integral domain, which we'll call capital D here. Now remember, an integral domain is a commutative ring, which is not the zero ring, so it's a non-zero commutative ring, such that a certain special property is obeyed. And that special property is that if you take any two non-zero elements from the integral domain and multiply them together, the answer, whatever you get, will not be the zero element. In fact, the only way of multiplying two elements of the integral domain together and getting the zero element is if one or both of the things that you're multiplying together are themselves the zero element. Okay, so we're going to take an integral domain, and we know that in the case of finite integral domains, they are already fields. But in the case of infinite integral domains, such as the ring of integers, they are not necessarily fields. And what we're going to do is we're going to construct a larger structure, okay, which will be called the fraction field. Okay, so we're going to construct a field which we'll call capital F here, which is going to contain the initial integral domain. So the integral domain will be contained within the fraction field, and which is a field, of course. So we're going to show that any integral domain can in fact be thought of as sitting in a larger algebraic structure which is a field. Okay, you can always extend an integral domain up to produce you a field, and this field is called the fraction field. Okay, now to give you some more insight into this, there is a very notable example that everyone's familiar with, which is if you do this for the integral domain which is the integers. Okay, so this very notable example of an integral domain which is the integers, if you construct the fraction field for the integers, you end up with the rationals. Now, of course, you can think of the integers as being within the rationals. All of the whole numbers are within the rationals, but the rationals is much bigger. Okay, so this is in fact a proper subset. The rationals contains things like a half, a third. Okay, so you have multiplicative inverses for all of the elements in the integers that you didn't previously have multiplicative inverses for. Okay, so you construct a larger algebraic structure which is a field, and this is called the fraction field. So the rationals is the fraction field for the integral domain of the integers. Okay, so what we want to do is look at this formally, but we're going to do it in more generality. Okay, so we're specifically going to look for an arbitrary integral domain at how you construct a larger algebraic structure which contains the initial algebraic structure, but which is a field rather than just an integral domain. Now, I should just make a point here. Okay, when I say that the integral domain is going to be contained within the fraction field, or that the integers are contained within the rationals, really, more strictly, what I should say is that there is going to be an injective homomorphism, a very natural injective homomorphism from the integral domain into the field of fractions. Okay, so it's going to be possible to associate with every element of the initial integral domain a very natural element of the fraction field here. Okay, and addition and multiplication are going to be compatible between the two. Okay, so we're going to have a injective but not necessarily surjective homomorphism here, so a homomorphism onto a subset of the fraction field, and if you just restricted your attention down to that subset, of course it would then be an isomorphism. Okay, and this is effectively an inclusion mapping. So this is the formal way of saying that it's going to be included in there. There's going to be a very natural associative or associating map which can associate elements of the integral domain with elements of the fraction field. Okay, right, so what I now want to do then is actually look at how we can construct this thing. Okay, so we're going to motivate everything by thinking in terms of how we went from the integers to the rationals. Okay, so the way of doing this then is just to actually create fractions, okay, new symbols. So what we're going to start off by doing then is we're going to start off with our integral domain here. Okay, so this is just a set of symbols with an addition and multiplication law defined on it, and it's a non-zero commutative ring which obeys that special property that integral domains must obey. And I must stress that being able to construct a fraction field for your integral domain relies on it being an integral domain. You can't do this for an arbitrary ring, okay, and we'll see along the way why you rely on it obeying that property of integral domains. Okay, so here's our integral domain, and I'll just underline that in green. So, let's now attempt to create our fraction field. So let's just go about this very bluntly, okay? So what do you think, intuitively, you're going to have to do if you want to construct a field of fractions, or a fraction field? Well, you're going to have to start by just creating a set of fractions, like you did in the case of the rationals. Okay, so you want fractions, basically. You want to create symbols that are fractions where you have a numerator and a denominator, and the numerator is an element of the original integral domain, okay, in this case the integers, and the denominator is an element of the original integral domain, in the case of the rationals, again, an integer. Okay, so that's where we're going to start off now. I'll give it away right now. This isn't going to be the set we will use for our fraction field, but it's a good starting point, certainly. Okay, so I'm not going to call it F, I'm going to call it S instead. Okay, and it's going to be the set that contains all fractions. So it's going to just be all symbols of this form, and that's what you have to think of these as. We are just creating new symbols here. Okay, we have not defined this to mean anything else. Okay, so you have to abandon your preconceptions from classical algebra now and just think abstractly. We are just creating symbols. We're going to define it to have incredible structure, and it's going to go back to working the way that you know that it works from your understanding of classical algebra, but at the moment we're just creating symbols. So all I've done here is I've taken one symbol from my integral domain here, I've then put a line underneath it, and then I've put another symbol underneath it, and we'll call the symbol on the top the numerator, and we'll call the symbol on the bottom the denominator. Okay, so we're creating things of this form where A is an element of the integral domain and B is an element of the integral domain, except there's going to be one thing that I do not want B to equal, and that's going to be the additive identity. I'm not going to let you put the additive identity in the denominator's position here. Okay, and that should, you should have good intuition as to why I'm not going to allow you to do that from your understanding of the classical case of taking the integers and turning it into the rationals. We'll see where we rely on the fact that the denominator is not going to be the additive identity later on. Okay, so we're just creating all of these symbols of this form, an element of the integral domain over another element of the integral domain, but this bottom element cannot be the additive identity. Okay, so we've got a beautiful set of symbols here, and we will call these symbols of this form, i.e. something over another thing from the domain, we will call them fractions. Okay, so that's the formal definition of a fraction. It's just a symbol. Okay, that's all it is. Okay, so this is a fraction where you've got one element of the integral domain over another element of the integral domain. That's the formal definition of what a fraction is. It's just a symbol at the moment. Okay, right, so now you might be expecting me to now just define an addition law and a multiplication law on this set of symbols and then turn it into a field like magic, but I'm not. Okay, I am not going to define an addition and multiplication law on this set of symbols. I'm going to refine this slightly before we actually do that. And to motivate what needs refining here, let's think about the case where we have the integers as our integral domain, and then we're trying to construct the rationals. Okay, so if we construct this set, capital S, where our integral domain here is the integers, so imagine sticking in for D here, the integers, then let's think about the things that we will get. Okay, so for instance, we will get things of this form. We'll get 1/2. Okay, that's certainly going to be an element of this set that we've created where our integral domain was the integers, because that's just 1 on top and 2 on the bottom, so that's brilliant. We'll also get things like 1/3. Okay, so this is going fantastically. Okay, now I'll show you the catastrophe. The catastrophe is this: we'll also get 2/4. Okay, and you will say from your classical understanding of how algebra works, of how the rationals works, okay, how this field of fractions from the integers actually works, you'll say, but that one's the same as a half. Okay, that's not a problem, but it is a problem. Okay, because in this set of symbols here, there is absolutely nothing telling me that this one is the same as this one at the moment. I haven't defined any such equivalence yet. Okay, so we haven't got that structural understanding that this symbol is the same as this symbol, because they're not the same. They are different symbols here. This symbol is different from this symbol. Okay, so what we now need to do is we need to take this set and put some structure on it that that corresponds to this equivalence of certain fractions. Okay, so we want this fraction to be considered equivalent to this one, and in this set that we've got so far, they are not equivalent. Let me make that very clear. They're not equivalent at the moment. They are distinct elements in this set, and if we were just to define an addition and multiplication law on this, they would stay different elements. Okay, so I need to put some sort of equivalence relation on this, okay, so that I group together all of the fractions which I want to be considered equivalent, and I consider that subset of this set capital S of equivalent fractions now as one element, and that's what we have to do now, and this is the most complicated bit of the entire video. Okay, the field of fractions, or the fraction field of an integral domain, is not going to be this set. Instead, it's going to be the set of equivalence classes of this set. So we are going to partition this set up into lots of little subsets. So to draw a picture of this, here is our great big set capital S here. Okay, and what we now want to do is we want to partition it up into subsets. Okay, so we want to chop it up like so into subsets, and we want these subsets to contain all fractions that we are thinking of as being equivalent, like a half and 2/4. They'll be together in the case of the integral domain being the integers. So let's take the example of the integral domain being the integers for our picture here. So we want a half and 2/4 to be together, and all the other equivalent ones. So for instance, if we then go for 4/8, for instance, there's another equivalent fraction. Okay, we want that to be in there as well, etc., etc. So we want to form these equivalence classes, which are subsets of the set capital S, which contain all equivalent fractions. So all of the fractions in this subset are going to be utterly equivalent to one another, and we want that entire subset of S, that entire equivalence class, to now be an element. That's the mathematical structure now that I'm going to use. Not all of the individual fractions, the entire set of equivalent fractions. Okay, so the fraction field then, F, is going to be made up of these equivalence classes of equivalent fractions, rather than being this. So instead, the fraction field will be made up of lots of subsets of this set capital S, which are the subsets which contain equivalent fractions, and overall they completely cover the set capital S. And that's the structure, that much more complicated mathematical structure. That's the structure that I'm then going to define addition and multiplication on, and incredibly I'm going to be able to make it a field. Okay, right. So before we go any further though, we need to actually discuss how we're going to define this equivalence relation. Okay, and this is complicated. This is complicated set theory now. Okay, equivalence relations then. So equivalence relations are these relations which need to satisfy a bunch of axioms, and if they do satisfy a bunch of axioms, they will then successfully partition up the set capital S, and I'm going to show you how to do this. Okay, right, so we are going to define an equivalence relation on this set of symbols. Now let me just remind you of what an equivalence relation actually looks like. So let me take a very simple set here. Okay, so let's take a very simple set which I'll call S here. Okay, so this is just a bit of a reminder of set theory. Okay, and let's say it's just a very simple set. It contains 3 elements here, A, B, and C. Okay, then what an equivalence relation is going to look like is it's a table like so, and we notate it by this wriggle here. Okay, so I'll just colour this in green, and what we have to do is we have to give all of the elements of the set a row and a column in this table. Okay, so we'll give them all rows and we'll give them all columns, like so. Okay, so we'll then get a table which has 9 entries in it here. Okay, and then what you have to do in each of these entries is you have to put a tick or a cross. Okay, and if you put a tick, it will mean that the two elements are related to one another. So if I put a tick there, it will mean that A is related to B. So you can write this, A is related to B. If I put a cross there, it will mean that A is not related to C. So you can't write A is related to C. So you can't write A is related to C like that. That wouldn't be true. Okay, and then you just go through and define which things are related to what. Okay, so that's what an equivalence relation truly is in its most crude form. It's just a great big table of ticks and crosses in this way. Okay, now equivalence relations can be used to partition up a set, capital S, such as this set is what we're going to actually use it to do, provided that this equivalence relation obeys certain properties. You can't just put the ticks and crosses however you like, okay, because of course I could make this up, I could stick them wherever I like, I could just go along and do it randomly. If you do that, it probably won't be an equivalence relation, it probably won't be useful for partitioning up a set, capital S. So there are a bunch of axioms that we want an equivalence relation to obey if we can use it to partition up a set. Okay, so they all have fancy names, but they're incredibly simple. So axiom number 1 is reflexivity. Okay, or rather, maybe I think I'll just, instead of calling it reflexivity, I'll just call it reflexive. Okay, so we want the equivalence relation to be reflexive. Okay, now what does reflexive mean? It means that all elements of the set, okay, so for all A is an element of the set, capital S, it should be the case that A is related to A. Okay, and now what that means is that in this table we need to have ticks on all of these diagonal boxes here on the diagonal line there. Okay, so A needs to be related to A, B needs to be related to B, C needs to be related to C, and if you had a bigger set, they'd all the elements would have to be related to themselves. So you'd have to have ticks in all of these boxes down that diagonal line there. Okay, and that's what is meant by the reflexive property of an equivalence relation. Okay, so it needs to be reflexive. Symmetric is the next property that it needs to have. Okay, so it needs to be symmetric. Now, what does symmetric mean? Symmetric means that if you have stated that A is related to B, it must also be the case, okay, so if A is related to B, it must also be the case that B is related to A. Now, what that means is that the table here is going to be symmetric down the diagonal line. So we've said A is related to B here, so we now need B to be related to A. So we're going to need a tick in this box here. Okay. Equivalently, if A is not related to C, then it's also going to have to be the case that C is not related to A. Okay, because if C was related to A, then it would imply that A was related to C by this symmetric property here. Okay, so we need the ticks and crosses to be symmetric down the diagonal line, basically. Okay, right. And then the final property is that we also need it to be transitive. Now, this is the most complicated but incredibly powerful property. Okay, now transitive means that if A is related to B, okay, so if A is related to B, I'll just put an if here, if A is related to B and B is related to C, then it must also be the case that A is related to C. Okay, so if A is related to one thing and this other thing is related to a third thing, then it must mean that the first thing is related to the third thing as well. Okay, now this is actually going to determine what we're going to have in these two entries here. Okay, because I have said that A is related to B, but A is not related to C. So when I ask the question, is B related to C, the answer must be no. Because if I stuck a yes in there, if I said that B was going to be related to C, then since I know A is related to B and B is related to C, it would have to be the case that A is related to C, but I've already said that A is not related to C. So that forced me to put no in both of those there. Okay, and I think what I have just drawn you there is in fact an equivalence relation. Okay, so transitive is an important property, and we're going to see how important it is there. So that's just a little bit of a reminder about what a equivalence relation is. Okay, so if you have defined a table like this that does obey these three axioms, then we call this an equivalence relation. And what I'm going to show you is that actually we can use an equivalence relation of this form to partition up a set capital S. But before we actually do that, instead of just talking about a set of three elements, let's go back to the set that we want to actually work with, this set of fractions. Okay, so let's define an equivalence relation on our set of fractions. Okay, so when do I want a fraction a over b to be related to another fraction a prime over b prime? Okay, so I'm trying to create an equivalence relation, and I'm going to put yes if they are intuitively equivalent to one another. Okay, so if, for instance, so I'd say that a half was equivalent to 2 over 4, they were related to one another. So I would put a tick between these two symbols here, okay, whereas of course a half is not equivalent to a third, so I put a cross if I was asked a half and a third. In the entry corresponding to a half and a third, I put a cross there. Okay, right, so how am I going to decide whether one fraction is equivalent to the other? What criterion can I come up with for someone who's trying to draw out this great big table? Okay, and indeed I might actually draw out this table just for intuition here. Okay, so we're trying to define an equivalence relation. We will give all of the elements of this great big set of fractions here a column, and we'll give all of the elements of this great big set of fractions a row here. Okay, and now what we will have to do is go through and fill in all of these entries with a tick or a cross. So what I need to now do is give someone a rule for actually doing it. Okay, so I'm going to make a rule, and then someone could go away and actually draw out this great big table, or we could get a computer to do it. Okay, so how is it going to work? What rule am I going to come up with? Okay, so the rule that I'm going to use is I'm going to say that they're going to be equivalent if it's the case that this numerator of this one times the denominator of the other one here is equal to the denominator of the first one times the numerator of the second one. Now just take a minute if you like, to think exactly why this captures the normal notion of equivalence of fractions. If we take a half and 2/4 here, okay, why are they going to be equivalent? Well, if I take the numerator here and multiply it by the denominator here, that's a times b prime here, we'll get 4. If we take then the denominator here and multiply it by the numerator here, that's b times a prime, we'll also get 4. So they satisfy this condition, and indeed this condition does capture the intuitive concept of two fractions being equivalent to one another. Okay, so this then gives you a way of working out whether any two fractions are equivalent to one another. And someone could now go through and go for every single one of these entries here and work out whether it's going to be a tick or a cross. What I need to do is now make sure that the table that they will get using this rule, okay, actually is going to obey these three axioms here. And I'll just stress it again, to decide whether you're going to put, and I'll just actually even draw this out even better. Okay, so let's say this is the row corresponding to this fraction a over b here, and let's say this is the column corresponding to this fraction a prime over b prime here. Okay, so if you want to decide whether we're going to put a tick or a cross in here, you have to ask, is this relationship true? Multiply the numerator by the denominator here, multiply the denominator of the first one by the numerator here. If you get the same answer, put a tick in. Okay, if you don't get the same answer, put a cross in. Okay, that's how you work out whether it's going to be a tick or a cross there. Okay, so someone could now go through every single one of those entries and work out whether it's going to be a tick or a cross and draw me out a table. I now need to make sure that the table I get will obey these three axioms here. Okay, so that I can make sure it's an equivalence relation, and then I'll show you why having an equivalence relation which obeys these three axioms allows us to partition up the set. Okay, so axiom number 1 then, reflexive. Okay, so I hope this should be pretty obvious. So if I have one fraction, a over b, and I'm asking, is it related to a over b? Okay, it is going to, and I should just put if. Okay, a over b will be related to a prime over b prime if this is true. Okay, so is it the case that a over b is related to a over b? Okay, well, it's going to be true if this is true. Okay, so take the numerator here, multiply it by the denominator here, you'll get a times b. Take the denominator here, multiply it by the numerator here, you'll get b times a, but of course in the integral domain here, multiplication is commutative. Okay, so these two things are exactly equal to one another. Okay, so that's absolutely fine. So indeed, all fractions will be related to themselves. So you'll have ticks all along the diagonal entries in this relation table here. Symmetry. Is it going to be the case that if I have a fraction related to another fraction, that I can put it the other way around? Okay, so what I want to now ask, so this was reflexive. Okay, now what I want to ask is if I've got it the case that a fraction a over b here, and I'll just move this up, is related to a prime over b prime. So I'm telling you this is true. Okay, now is it then the case, so now I'm asking the question, is it the case that a prime over b prime is related to, and I'll put a question mark there, a over b? Okay, so if this is true, is this true? Well, for this to be true, it needs to be the case that a prime over times b, so the numerator here times the denominator here, is equal to b prime, the denominator here, times the numerator up here, a. Now, why is that going to be true? Well, if we go back here, the condition that must have been true for this to be true is that the numerator here times the denominator here, a times b prime, must have equaled the denominator here times the numerator here, b times a prime. Okay, so if a over b was related to a prime over b prime, then this must have been true. If we want a prime over b prime to be related to a over b, then this better be true, but of course those two statements are exactly equivalent, again because of commutativity of multiplication in the integral domain. So b times a prime is the same as a prime times b, and a times b prime is the same as b prime times a. Okay, so that's absolutely fine. If this is true, this is also going to be true. So symmetry has hold true. Now transitivity. Okay, and this is the most difficult one, but it's still not too difficult. Okay, so if we have it the case that a over b is related to a prime over b prime, and we also have it true that a prime over b prime is related to a double prime over b double prime. Okay, so these two things are true. The question is, can we conclude, does this imply that a over b is related to a double prime over b double prime? So if I know these two things are true, is it the case that this is true? Okay, that's what we now want to ask, okay, with this definition of relativeness. Okay, so, or equivalence rather. Okay, so, if we know that these two things are true, what do we know? So if this is true, then we know that a times b prime, so the numerator here times the denominator here, is equal to b times a prime, the denominator here times the numerator here. If we know that this is true, then we know that a prime times b double prime is equal to the denominator here b prime times a double prime. Okay, so those two things we are given. They must be true if this is going to be related to this and this is going to be related to this. Now the question is this related to this? And what do we need to prove if we want to say that this is going to be related to this? Okay, so this will be related to this if a times b double prime, so the numerator times the denominator, is equal to the denominator of the first one times the numerator of the second one, b times a prime here. Okay, right. So, what we need to prove is that if these two things are true, this one is also true. So how does this work? Okay, so what we're going to do is we're going to take this relation here. Okay, now if this relationship is true, I can multiply both sides by, let's say, b double prime. Okay, so if this is true, it's also true that a times b prime times b double prime is equal to b times a prime times b double prime. Okay, perfectly valid. If this is true, then this is also going to be true. I've just multiplied both sides of the equation by b double prime. So if this was equal to this, then when I multiply both of them by b double prime, it should still be an equivalent, an equals. Okay, right. Now what I can use is the fact that I have this relationship is true here, and look what I've got here, a prime times b double prime, so I'm going to now replace that with b prime times a double prime. Okay, really I'm using associativity of multiplication here. I haven't even bothered putting the brackets in there, but the brackets were around b times a prime, okay, and then I've multiplied by b double prime, so what I'm now using is associativity of multiplication. Okay, and now I can replace a prime b double prime with b prime times a double prime there. And then what I'm going to end up with here is A times B prime times B double prime is equal to B times B prime times A double prime. Now, here's where I use the fact that it is an integral domain, okay? And it's also where I use the fact that B prime is not equal to 0. So remember, the denominators cannot equal 0, so that tells me that B prime and B double prime are not equal to 0. I actually am only going to use that B prime is not equal to 0. I'm also now about to use the fact that this is an integral domain. Okay, so it obeys the cancellation law. So if I've got B prime in both of these here, so what I can do is just apply commutativity and associativity of multiplication to turn this into B prime times A times B double prime there is equal to, and then I'll have the B prime out the front again, times B times A double prime, like so. Okay? Right. And now what we can do is apply the cancellation law that holds true in an integral domain. So because B prime is not equal to 0, you can conclude from this statement here that A times B double prime is equal to B times A double prime. Okay, you can't do that in an arbitrary ring. Okay, you can only do that because it's an integral domain, and it also relies on B prime not being equal to 0. So that's the cancellation law that holds true in an integral domain. Okay, so what I've now shown you then is that this equivalence relation does obey transitivity. So I have defined a good equivalence relation on my set, capital S. It obeys all three of those axioms, and now what I can do is use this to partition up my set, capital S, into equivalence classes. Okay, but we'll have a break here and do that in the next video.